ready.
Okay. Good afternoon, good morning, or good evening, according to your time zone. I hope that you can see my slide in presentation mode. And I would like to thank Benjamin and Manfred for giving me this the opportunity to share with you our findings. Of course, this is not a one-man show, but I will present some work that we are doing alongside with Sara Galeazzi, that is a PhD student that now she is spending a visiting period at USGS, and Francesco Ponziani, who is the responsible for the Umbria Region Civil Protection Service and the one that is involved in the landslide assessment. Just a few words about me, just to introduce myself. As already been pointed out, I'm a researcher at the Research Institute for Geo-Hydrological Protection at the National Research Council of Italy, and my research interests are related mainly to the use of remote sensing data to satellite data, mainly related to soil moisture and precipitation for hydrological applications and natural hazard mitigation. As I pointed out, this work is carried out in collaboration with the Civil Protection Service of Umbria Region, that is an authority that is in charge for the daily assessment of natural hazards over the regional territory. Here you can see Italy, and Umbria is located in the central part of the country. The assessment is carried out on a daily basis through a suite of models or tools that have been defined and calibrated over the region, over the territory. For what concerns the landslide assessment, this work started more than 10 years ago during my master thesis, and basically what we tried to do was the development of some soil moisture related rainfall thresholds for the activation of the landslides, because there was the feeling that, of course, the soil saturation conditions play a key role in the activation of the landslides. Here you can see the result of the historical analysis we carried out in 2012, and basically we analyzed some rainfall, some landslide activation data that we had over the region. Maybe I can, okay, use the pointer over the region, and for each of these landslide, what we did was the simulation of the soil saturation condition through a simple hydrological model, and we extract for each event the antecedent soil saturation condition and the accumulated rainfall over different accumulation times. In particular, was selected 24, 36, and 48 hours of cumulated rainfall, because this interval was, let's say, were suitable for the assessment carried out by the civil protection. And what we found was that for wetter soil condition, we require a smaller amount of rainfall is required to trigger a landslide. And moreover, as you can see here, yes, most of the events were clustered here in this mid to wet condition. But in any case, we can see that, for instance, we can observe landslides even if the soil is very, very dry. But we need a lot of rainfall. And this analysis allowed us to draw this to identify this threshold that is used for the assessment for assessment of landslide hazard. The assessment is carried out by considering the overcoming of this threshold, by considering the weather forecast provided to the Civil Protection Service, and basically, if we have a point that is overcoming a threshold, we can define an issue for that particular grid point. According to the colors, to the situation that the civil protection operator found, he can assess the landslide hazard condition throughout the region. This approach has two main limitations, at least the one that we would like to work on, that were the two coarse resolution. The analysis was performed at a 5 kilometer of spatial resolution, and there were a lot of false alarms. So every time we observe rainfall, basically we have the overcoming of this threshold, and the office was forced to issue an alarm. But of course, a lot of times there was a false alarm. So basically, what we have done was reproducing the same analysis we carried out some years ago, and to do this, we considered a new landslide activation catalog available over the region, and we focus, of course, only on rainfall-induced events that can be observed during the major and widespread rainfall events occurred over the region, focusing only on shallow landslides. We use the rainfall and temperature data obtained through the regional monitoring network that have been interpolated over a 1 kilometer grid, in contrast of the 5 kilometer grid that we used in the previous version. And we use the hydrological model to estimate the soil saturation condition at each landslide site. The model parameters have been obtained as a function of the soil textural class according to a map that we realized over the region. And here on the right side of the slide, you can see the comparison of this model data against in situ station, as you can see here, or by comparing the soil master simulation against satellite data, in this case, the soil master observation obtained through ASCAT sensor. And as you can see here you can see the Pearson correlation map obtained through this comparison. The two observations are in very good agreement. This could be also of interest because we can notice some let's say some deviation from the let's say from the reality if this correlation goes down. We changed the approach used in the previous version. Instead of considering the cumulated rainfall at fixed temporal interval, we decided to develop a tool that is able to define and to extract every single rainfall event occurred during the time period, and for each event, basically what we extract was the soil saturation condition at the start and at the end of the rainfall event, and of course the total amount of rainfall falling during the rainfall event. The closest rainfall event to the activation date that we had in the catalog was used as the triggering one, used to define the threshold, while the others are used to perform the non-event analysis in order to control also the number of false alarm. So just to wrap up a bit the methodology, what we have done was we collected all the rainfall and temperature data over the region to force a soil water balance model that has been parameterized by considering the soil textural classes over the region. each of the almost 600 landslides that we collected in the period 2019-2020. For each of these landslide events, we simulated the, the soil saturation degree, and we extracted all the rainfall events occurred at that particular site, identifying the one that likely triggered the landslide event. Then we make some analysis in order to search for a threshold, a rainfall threshold that was, let's say, similar to the one we obtained in the past, or maybe something different related to, I don't know, different features like the slope, the rainfall regimes that can be observed throughout the region or so on. Well, unfortunately, we didn't find any clear relationship between rainfall and antecedent soil saturation condition by analyzing all these events. The only finding that we can observe here in this left graph. Here you can see the antecedent condition and the total rainfall fallen during the event. Was that most of the landslide occurred where the soil is in mid to wet soil saturation condition. This is of it's not useful for the Civil Protection Service, because we can simply say that when the soil is wetter than, I don't know, 0.60%, this is wetter than the 60%, then you can issue an alarm. Otherwise, we will be in alarm every day in the period October to April, for instance, and so it's not visible. And even taking into a look at the saturation change occurred during the event was helpful. Also, in this case, we observe a cluster of the event in this portion of the graph. So we need to take a step back and try to identify if we were missing something, or we are wrong somewhere. But we found that there are, in the literature, there are several examples about the role of the soil saturation on landslide activation. And so maybe what we should do is just to we need a change in the point of view. And this is what we have done. So basically, we take advantage of these two studies in order to identify not only how much rainfall is fallen during that particular event, but what that rainfall created within the soil. So not just the total amount of rainfall, but the antecedent saturation and the saturation change that we observe at the landslide site. And this is what we found. Here you can see this graph in which here you can have the antecedent saturation and the saturation change on the X and the Y axis. And what we found is that the solid, the filled points are represent a landslide event, while the yellow circles the non-triggering events. What we have found is that most of the landslides fall within this band that was the close to saturation, this close to saturation band. This means that basically we can observe a landslide even if the soil is close to saturation at the beginning of the rainfall event, or if we observe an increase in the soil saturation that can bring that point close to full saturation condition. So far so good. We have found something that can be useful for the civil protection, because they can assess the hazard by using this approach. So if the point is falling into this band, they can really issue an alarm. But the point is that a lot of non-triggering events fall in the same area. As you can see here, basically this area is completely gray, so it's full of non-triggering events. And in this way, we are not able to reduce the number of false alarms that was characterizing the the first version of the model. And moreover, we are completely blind of when it continues to rain and the soil already reaches saturation. We don't know what is going on. So we take advantage of this first preliminary results, and what we thought was that we can estimate the amount of water that is needed to that particular point to reach saturation as a function of course, of the actual soil saturation condition and the hydraulic parameters. And then we can estimate the amount of rainfall that is infiltrating into the soil. If this amount of rainfall that is falling into the soil is greater than this amount of rainfall that is needed to the soil to reach saturation, we can observe a landslide activation. And we observe, yes, a stable condition. So basically, this is the results that the preliminary results that we obtained. Here on the x-axis, you can see this critical rainfall. That means the amount of rainfall that is needed to the particular point to reach saturation. And here, the rainfall that is fallen during that event that can actually infiltrate into the soil. The black crosses represented the landslide events, while the green circles all the non-triggering events that we extracted throughout the analysis period. And here you can see that we have to reduce a bit the amount of landslides, because we found some troubles in 14 data, if I remember correctly. But in any case, we were able to extract more than 1 million rainfall events. And basically, the model correctly identify a landslide when this cross overcome this the blue line, that is the new proposed threshold. And yeah, you can see that in any case, the model is characterized by good performance with a probability of detection of more than 70% and a very limited amount of false alarms. The threshold has been validated and been compared to the previous ones used in the first version of the model. And here you can see basically the same graph I was showing you before. Here we have the saturation degree, and here we have the accumulated rainfall at different accumulation times, 24, 36, and 48, as I said before, by using the same methodology. So we extract all the rainfall events according to, in the first case, according to the tool that we developed, and in this old, let's say, approach by comparing the amount of rainfall fallen in the following 24, 36, and 48 hours, in which we used to start we select the initial saturation degree, I'm sorry. And we can observe that we can catch more landslides that compared to the previous model. But more, I think that also something very important is that we can observe a strong reduction of the false alarms. And this is something that is very, very, very important. Yes, here you can see the same results in terms of categorical scores or in terms of probability of detection and false alarms. And moreover, in order to not consider let's say, the amount of the total rainfall events that we extracted, because they are more than 1 million compared to only, let's say, 600 landslides. So there is a big mismatch about the numbers. What we have done is to extract 100 times. I extracted 1,000 non-triggering events completely randomly, in order to create a subset of this event of 1,590 events. And here you can see the assessment carried out on this subset in order to take into account, as I said, the the numbers, and here you can see that in any case we perform the new model performs very well, perform way better than the previous one. Here you can see the graph in terms of false alarms and threat score for the new the four different thresholds. We have validated this approach by using different rainfall products, because what is important is just to force the model, the hydrological model, with certain kind of certain rainfall input. And here you can see the results in terms of in identifying the landslides event by using a product that is based on integration of rain gauges and radar observation available over Umbria region for a subset. The period is 2012-2020. So we have also a limited amount of landslides, but you can see also in this case we obtain very good results. And we have done the same also by using satellite rainfall data, in this case the iMerge early run product. Here we can observe better detection capabilities, but we observe also an increase in the false alarm ratio. I think that this is very interesting, because the methodology can be applied with every kind of input rainfall input data that we want to use, without the need of recalibrate again the threshold. What we need is just to force the hydrological model with the same input, the same rainfall that we used then for estimating the event rainfall. In the time that we were working on this model, of course, we observed also some limitations about the proposed approach. First of all, the first one is that, as you can see in the previous slides, the number of false alarms is still quite high, and we need also to increase the detection capabilities. But one of the key limitations of this approach is that is based on the amount of rainfall that is infiltrating into the soil, and this could be impacted by high intensity rainfall events. Here you can see a storm that hit Umbria region last year in June 2023, and we observed more than 100 millimeters fallen in 2 hours. And of course, it created a flash flood in the area. As you can see here on the map on the left, the storm is very localized. Is a typical storm, summer storm that can act here in Italy, and was very intense and very localized. And here on the right side, the left side, I'm sorry, you can see the assessment carried out by using the first version of the model. Here you can see basically here when you see the yellow points, that means that we have that means that the threshold is over, the point was over the threshold, both considering different forecast length. While in the proposed approach, as I said, is limited to the amount of rainfall that is infiltrating into the soil, and high intensities means that we have a smaller amount of rainfall that can infiltrate into the soil, and these are the results. So we have just a few points over the threshold that's represented here in the map. So we are now considering different options in order to solve this issue, this problem, because it's something that is happening in we had a couple of storms like this, one in June and one in November, and we observed the same behavior. So we have to find out a way to solve this problem. And this was my last slide. Here the reference that I cite in the presentation. And thank you very much for your attention. Here you can find also my contact in case you want to keep in touch. Thank you.